except I won't be here Thursday. So I'll put it to you all. I think either way is fine with me. I can either Zoom, and we'll make it synchronous on Thursday during class, or I can just make a video and not make it synchronous and accept the fact that only 10% of the room will watch it. So what would you rather have? Would you rather have Zoom or a video?
Video.
Oh, you got one for video.
Video.
All right, hands, video, Zoom. Well, the videos have it. I know, 'cause you can't do Zoom on twice the speed, can you? I get it. Y'all are gonna have to know the stuff though. And I don't, the two lectures I videoed that you all didn't watch hurt you on the exams. Those of you who didn't watch it definitely got hurt on the exam for that, so. This is gonna be, you're gonna need this stuff for the lab. So you're definitely gonna wanna watch this video. Now, whether you pay attention to it or not, I guess it's all on you, which is fine. Okay, let us start from where we're doing threads, and then what we have here on the program, I have on the left side of the screen is a program where I'm gonna fork off a bunch of threads, okay? They are all sharing one of these, okay? And each one of them, everything's the same for every thread except for the threads have different IDs. One's 0, 1, 2, 3, etc. They're all running this code here, okay? Which is a big loop where they're going to go through the number of iterations. Then there's a shared string. They're going to go through every character of that string and change each character to be the letter capital A plus their ID. So thread 0 will set it to A, so thread 1 will set it to B, etc. We null terminate it and then we print it. Okay? And if we remember, and there's nothing that's forcing the threads to communicate with each other in any way. So the threads are just off running simultaneously, beating on each other, and I think we remember last time we compile this. Right, when we run it, if we run it with 2 threads, and let's go with a string size of 100 and 1,000 iterations, and we'll grep AB, right, we notice that there are a whole bunch of strings that have both A's and B's in them. That's because while one of them's printing it, the other one's stomping on it. Okay, so this is called a race condition. A race condition is when you have 2 threads accessing and modifying the same variables and their order is not deterministic, right? The order can change. That's what makes it a race condition. Race conditions are typically bad because typically you want your programs doing something deterministic. Now you'd like your threads to be working off in parallel, but you don't want to have race conditions. And one way to help mitigate race conditions, did I go through a mutex before? I did not. Okay, so there are 2 data structures we're going to learn to help with synchronization. One of them is very simple. It's called a mutex. You can also call it a lock. So if we do man pthread mutex lock. Okay, so your mutex is a data structure here, defined in pthread.h. Okay, it's pthread mutex t. And you have 3 operations that you do on it. One's called initialize, where you just initialize it. You pass a pointer to it, and then that'll set its state. Then you have lock and unlock. Now, what lock does is you call it, and you give it a pointer to the mutex. Now, what will happen is the thread system will guarantee that when this returns, then any other thread that's trying to lock the mutex will be blocked. Their lock call won't return. Okay? So only one thread can own or lock the mutex at any one time. So when you call this and it returns, now you've got the mutex and no other thread can lock it. If a thread does try to lock it, it's going to block. Right? You own it until you unlock. Okay, by calling pthread unlock, mutex unlock. And then what that does is that will release the mutex, and if another thread or if a whole bunch of threads are trying to lock it, they're all blocked. one of them will get it and unblock, and it'll return from its pthread mutex lock call. Okay? So this gives you a synchronization point for your threads in that you can make your threads cooperate, so using mutexes, so that you can guarantee that only one of them might be executing a piece of code. Okay? So let's look at this. Let's go back to this race condition code here, and let's put a mutex in there. So circ race 2.c. Let's go ahead and put a mutex in. So here, pthread mutex t star lock. Okay. Let's go ahead and create it. Let's get ourselves another pthread mutex t. I'll just put it on the stack here. We'll call it lock, and then here we can say ti dot lock equals lock. Okay, so they're all getting a pointer to the same variable that's sitting there on the stack. Now I could have mallocked it and put it on the heap if I wanted to. Right. Either way. Now what I also need to do is I need to initialize it. So I'll say pthread mutex init lock null. Just give it null. Okay. And now inside here we can do a couple things. Let me go ahead and we'll lock the mutex here. So here I could say pthread mutex lock t s, no, not s, t lock. I think it only takes one man pthread mutex. Yeah, it just takes the mutex. Okay, so I'll lock it here, and then I'll unlock it here. So what effect is this going to have? Well, whatever thread gets the lock first, okay, if you have competing threads, whatever thread gets the lock first is going to do all of its print statements before it unlocks the mutex. So whatever thread gets it first is going to run all of its iterations to completion. And then when it's done, it'll unlock the mutex, and the next thread will get control, etc. Okay? So here, let's... All right, so here, let's do 4 threads, string size of 50, and let's do 3 iterations. Okay? Now what's going to happen is one of these threads will get control first, and when it does, it's going to run all 3 of its iteration before any other thread gets control. Right? So thread 0 gets control first, does everything, then thread 1, then thread 2, then thread 3. It's not guaranteed to go in that order, although it sure feels like it right now, doesn't it? Oh well. Okay. Now, if I instead put the lock and unlock calls here, right, now the threads can alternate on lines. Right? When thread 0 gets control, it'll print out its first line, but then it'll unlock the mutex and another thread can get control. Right? So you'll notice, right? Thread 0 ran twice, and then thread 3 ran, then thread 1, then thread 2, and then thread 0 again. These things, right? Thread stuff, you can't be guaranteed what order is going to be. Right? So here it's very similar, only now thread 0 got control here. When I call pthread mutex lock, you can't say, well, if I fired off thread 0, 1, 2, and 3, thread 0 is going to get it first, then thread 1, then thread 2. You can't make any of those guarantees. You just know, if I call lock, then eventually I'm going to get it. Okay? The key with this is, you'll note there's no interleaving stuff, and that's because no thread can go in there and start overwriting this, this buffer, because while this one's modifying the buffer and then printing it out, it owns the mutex. Okay. Now I'm going to say this multiple times. It's in the lecture notes in green. Okay. And in the lecture notes, it tells you to reread it. Okay. Now this comes from years and years of teaching experience in this class. You all get confused with mutexes. Okay. And here's how you get confused. you will say things like, I'm going to allocate a mutex and the mutex is going to lock out all the other threads. That doesn't happen. A mutex does not lock other threads. Right? A mutex is a data structure. And then they can cooperate on trying to lock the data structure. Okay? So in this code, okay, thread 0 is kind of locking out threads 1, 2, and 3, but the only reason it's locking them out is because they're all collaborating on a single data structure. There's nothing that thread 0 does to go proactively make threads 1, 2, and 3 block. As I said, I'm going to say this multiple times because I see this on exams all the time where you're like, well, I'll just put a mutex and that'll lock everything out. No, it won't. It's a data structure. You have a mutex, and the data structure is going to be what locks the other threads out because they collaboratively lock each other out. It's not, there's not that one forces another to be locked out. Okay. Is it just the end of the semester? I'm sensing no energy. None whatsoever. Okay. After lunch, end of the semester. All right. Yes, sir.
So, will the other threads like attempt to overwrite, and then they somehow know about the lock, and they?
So it's a good question. So again, just concentrate on this code. All 4 threads are running the same code simultaneously, right? So they're all going to call pthread mutex lock in some order. One of them will get it. That's what the thread system guarantees you, is that one of them will get the lock and this call will return. Then, until this thread goes and unlocks the mutex, all the other threads, if they're trying to lock it, are going to be blocked. And they're not going to return until this one calls unlock, and then one of them will return. Okay? So it's a collaboration on a data structure. And the data structure is this mutex. And the whole semantics of the data structure is that all it's got is lock and unlock. Right? So if I call lock, and I get it now, no one else will return from their lock call until I call unlock. And you can't force another thread to unlock a mutex. There's no, hey, get rid of this mutex. It might be there, don't use it. If you're writing that code, you're writing it wrong. It's just all there is to it. Right? If you call mutex lock twice, your mileage may vary, but your program will likely be buggy. So test the return values. I know I'm not. Test the return values because it'll find that bug for you. Yeah, I'll get you cold just a second.
Is the order non-deterministic because like right when it runs unlock, it's up in the air who gets to take it from there?
Kind of. I mean, underneath the hood, what's good? So underneath the hood, the simplest thing would be that your thread system just implements a vector, and when or a double-ended queue, and when you call lock, if the lock's there, you put yourself at the end and you take off whoever's at the beginning. But because these thread systems are written for machines with multiple CPUs, like my Mac's got 4 CPUs on there, I don't know how it chooses who to unlock. Sometimes they'll do something called affinity, where they'll want to unlock a thread that's on that processor. So it's up to the thread system to decide what to do. But the semantics are precise. Only one thread can own the mutex. Yeah.
So the terminology is kind of like heavy for me.
Okay.
So I'm going to give you an analogy, and you tell me if my logic is correct.
Okay.
So like if it's a band.
Wrong. Sorry.
If it's a band like playing music, unlocking it, like one of the threads returning is like it doing like a solo kind of. And
Right.
so this makes it so they can't do the solos at the same time, but they're still playing music but not doing solos.
Yeah, let me shift your analogy slightly. Right? Have you ever been in a group meeting where no one's allowed to talk unless they have the stick? This is very much like that, right? I get the stick, I can talk. You all can't talk because you don't have the stick. Now when I'm done, I'll put the stick down, and whoever gets the stick, now they can talk.
Okay.
So it's very similar in the soloing thing, but it's kind of like if I own the mutex, then I can solo and no one else can. Okay. Now, in the lecture notes, I go through another program that is very similar to try to hammer home this very same point. So let's just take a quick look at it. So this one's called mutex example. All right, and so again, we got to go through the code. That's the thing, the threading code. We have to go through all of our data. So the way I'm organizing this code is actually the way you should organize your code. This is how I should always organize thread code, right? And then I'm going to have data that is unique to each thread, and then in that I'm also going to have data that everyone shares. So what I have here is, here's a struct. Every thread gets its own one of these. Each thread will get its own ID, and then each thread will get the same pointer here to the shared stuff. So the shared stuff is all shared, right? And in particular, you know, the mutex is shared. Okay, and so now what this code, what these threads do, again, it's very simple. Okay, they're going to go to a while one loop. I'll just do it here. They're going to go to a while one loop. First thing they do is they're going to call pthread mutex lock to grab the lock. Right, so again, only one of them is going to get it. And then what the thread that gets the lock is going to do is it's going to increment the counter, okay? Set its own local variable to remember what the counter's value is, and then it goes ahead and prints itself out. Then it sleeps, okay, for some specified period of time, still owning the mutex while it sleeps. So no other thread, if they're all running the same code, then all the other threads are going to be blocked in their pthread mutex lock calls. Right? Then it wakes up, makes sure that the counter hasn't been changed from underneath it, which it shouldn't, and then goes on. Okay, it just does this loop over and over and over again. Okay, so if we run this, what is it? Okay, so here let's do it with 4 threads. And the U sleep time, that's microseconds. So let's have each one of these sleep for 1/10 of a second. Well, let's make it even slower than that. There we go. Okay. Oh, nice. Thread 0 is just... Aren't there 4 threads? That's interesting. No, thread 0 keeps getting the mutex. Okay. Now, I have a second piece of code here where I comment this out. So I'll just do it here. Let's comment out the lock and unlock. Now what's going to happen here? All the threads are going to run the same code at the same time, right? There's no mutex, so the chances are that one thread is going to update this counter while another thread's sleeping. And that thread's going to detect that right here, right? Because there's no protection on it anymore. Yep. So you'll know what happened. Thread 0 started, I love this stuff out of order. Threads are great, right? That's what we love, threads. Stuff's all in and out of order. But right here, when thread 0 woke up, when it went to sleep, its counter was 1. When it woke up, the counter was 4. And the reason is, again, the threads are now just, they're all beaten on the same data. Now, the last thing I do with this program, and here, let's just look at it. Okay, is I have one thread not play along. Okay, so I'm going back to the first program where all the threads are calling pthread mutex up here. They're all calling pthread mutex lock except for the last one. The last one's not locking the mutex. Okay. So when I run this, there's going to be a problem, right? Because thread 0 called pthread mutex lock, that, and as did threads 1 and 2, that's why you don't see them printed. Threads 1 and 2 are all blocking on their pthread mutex lock call. Thread 3 is not playing the game, not locking the mutex, and that's why we have the problem. And I do this again to underscore the fact that all your threads have to be cooperating in order for mutexes to work. It's not that mutexes magically shut stuff out. They're a data structure that gives you a synchronization point that you can use so you can give yourselves guarantees. So typically the way things work with threads and mutexes is if I want to update data that my threads are sharing, I'll do it while a mutex is locked, because that way multiple threads won't update the same data at the same time. So your pattern with the mutex is typically lock, update shared data, unlock, right? And if your threads, and if you want your, so for example, now where do we use threads a lot? One is user interfaces, right? If I have a user interface with a bunch of buttons and sliders, you'll allocate a thread to each one of those. And so what happens? You click on the button, it'll lock a mutex, update the state, and then unlock the mutex, release the button, now you can do it again, right? And so the mutexes allow you to deal with the fact that you don't want two things to happen to that shared data at the same time. If you're using threads for parallelism, okay, then what you want is you want the threads not to be all blocked in the same mutex, right? You want them to do their CPU activity while there's no mutex is locked, and hopefully you've set it up so they're not stomping on each other, and then when they need to update some data, lock a mutex, update the data, unlock the mutex, go. Okay? Is that gonna happen with you all? Yes. Your first threaded lab will be to write a chat server, I think, or is it the bonding lab? Oh, it's the bonding lab. Yeah, you're gonna have to do a bunch of stuff with that. The bonding lab is all about synchronization. Basically, you're gonna have threads that are either hydrogen or oxygen threads, and then you have to get two hydrogens and an oxygen to hook up together, and then say, hey, I've made a molecule, and then go away. And so, what's the mutex? Well, the mutex is gonna be shared data. What's the shared data? You might have a list of hydrogens and a list of oxygen threads. Right, and so you're gonna lock the mutex so you can say, well, what's the state? Who can I hook up with? And then once you figure out who to hook up with, you change the data structures. Now you unlock the mutex, and the threads can hook up. So it's fun. The chat server is much simpler from a synchronization standpoint. Your chat server, you have one server that is servicing multiple clients. And so a client can join the chat server. And so your main thread is going to need to keep a list of clients. And when a client joins, you're going to add it to the list. When the client leaves, you're going to take it away from the list. Well, that list, that you're going to have one thread managing that, and then one thread for each client. So when one client writes to you, then what you do is you basically say to all the other threads, hey, wake up and write the stuff to the client. Do I do it that way? No, I don't. I have one thread reading from each client, and then one thread that broadcasts to all clients. And so when a thread reads it, now it's going to set a shared data structure, say, hey, you need to send this to all the other clients. Here it is. Wake up. Mutex unlock, go. Okay. Possibly not a bad time for a clicker question.